Previously, we talked about selection combining, and in selection combining, we said that if we have two signals coming at two different antenna elements, let's say this is the first signal, and then we have another signal, and in selection combining, we select the best out of these two signals. And as a result of selection combining, there is a possibility that the selected signal is greater than the gamma threshold or the threshold value, or there may be cases where the selected signal is less than the gamma threshold. Particularly, let's say if this one is the gamma threshold, then there is a possibility that the selected signal is less than the threshold. So then we said that what will happen if we just combine the two signals, because it may happen that if we combine the SNR corresponding to the first signal and the SNR corresponding to the second signal, it may happen that the combined SNR is greater than the gamma threshold. So this is what we will see in this video. So let us say what will happen when we just combine the two signals. So we have signal received at the first antenna element given by y1 is equal to h1. h1 is the complex coefficient. Then we have multiplied by x, the signal, and we have receiver noise w1. Similarly, we have received signal y2 at antenna 2, which is given by h2x plus w2. So first let us compute the SNR corresponding to each of the branch. So let's say for this one, the antenna element 1, the SNR is the signal power divided to the noise power. So signal power, that means the variance of H1, which is equal to 2 sigma square. And then we have variance corresponding to the noise, which is sigma n square times Es, the signal power. Similarly, we will also get the same for the signal at second receiving element, 2 sigma square upon sigma n square times Es. So now we will try to compute the SNR of the combined signal. So the combined signal, we get y is equal to y1 plus y2. y1 is h1x plus w1 and y2 is h2x plus w2. We get h1 plus h2 times x plus w1 plus w2. So here what we can see is, first observation is that the noise is getting added. And the second observation is that we have h1 plus h2, where h1 and h2, they both are zero mean and Gaussian distributed. So then we want to compute the SNR of the combined signal. We compute the SNR corresponding to the signal part, that means this part, and then we divide it by the SNR power of the noise w1 plus w2. So we have expectation mod square of h1 plus h2. They both are independent, so we can write it like expectation of mod square h1 plus expectation of mod square h2. And this, the variance of h1, this is 2 sigma square, and then we have variance of h2, which is again 2 sigma square. So in the signal term, we get 4 sigma square. So basically, there is just the variance is getting added. So again, if we talk about the noise one, the variance of w1 is sigma n square, and the variance of w2 is again sigma n square. So in the noise part, we get twice sigma n square. So we divided, we compute the SNR 4 sigma square upon 2 sigma n square times Es. This 2 will get cancelled, so we will have 2 sigma square upon sigma n square times Es. So this is the SNR of the combined signal. But if you look at this SNR of the combined signal, this is exactly equal to the SNR of the first antenna and the SNR of the second antenna. So that means when you directly added the two signal, you do not gain anything, because the SNR of the combined signal is exactly similar to the SNR of the first antenna or SNR of the second antenna. So that means just directly add the two signals, we do not gain anything. So this is nothing useful to us. So we cannot directly add the two signals. So now, but what we want to see is that, is there any other way by which we can do this combining such that we add the two signals y1 plus y2, but we get the resultant SNR greater than the SNR of the first antenna or the second antenna? So the answer to this question is yes, we have a way, and it is called as cophasing. So in cophasing, you accurately estimate the complex rotation of the channels. So let's say we have y1 is equal to h1 x plus n1, and h1 is the complex coefficient, which is given by alpha 1 exponential of j phi 1. So that means the channel has provided a rotation of phi 1, and then we have a real valued gain alpha 1. So you estimate this rotation phi 1, and at the receiver side you apply this rotation as exponential of minus j phi 1. So similar when we have y2 is equal to h2 x plus n2. So let's say in this case the channel has provided a rotation of phi 2, and at the receiver side we will just multiply it by e raised to power minus j phi 2 y2. So in cophasing, what we do is we basically estimate the rotation provided by the channel, and at the receiver side we multiply it by the negative of this rotation. We again rotated the signal with the same rotation. So then we have y is equal to alpha 1 plus alpha 2 times x plus n1 exponential of minus j phi 1 plus n2 exponential of minus j phi 2. So how we have written this is simply just substitute this value y1 and y2 here. So you will get e raised to power minus j phi 1 multiplied by h1. What is h1? Alpha 1 e raised to power j phi 1 times x plus n1, and then we have e minus j phi 2 alpha 2 e raised to power j phi 2 plus n2. So this is y, received signal at the receiver. So you open the brackets, you multiply it, this term will get cancelled out with this one, this term will get cancelled out with this term, this is multiplied with the noise n1, and this is multiplied with the noise n2. So at the result you get this y is equal to alpha 1 plus alpha 2 times x plus n1 e raised to power minus j phi 1 plus n2 e raised to power minus j phi 2. So this is nothing but the rotation provided to the noise signal, but the power of the noise will not get affected because this is just a rotation. And this alpha 1 and alpha 2, they are the real valued. So again, we want to compute the SNR. SNR is the ratio of the signal power to the ratio of the noise power. So we have this expectation alpha 1 plus alpha 2 whole square divided by, again, the variance of n1 is sigma n square. We have variance of n2 as sigma n square. So this will, again, noise is getting added, so we will have 2 sigma n square in the denominator. So now we want to expand this numerator. So we know the expectation of alpha 1 square is equal to sigma square, 2 sigma square, and expectation, which is also equal to the expectation of alpha 2 square. And then we have expectation of alpha 1 is equal to sigma under root pi by 2. Oh, sorry, this is 2 pi. Yeah, this is pi by 2. So then we just substitute this expression into this following form. So we get 4 sigma square plus sigma square pi es divided by 2 sigma n square. And we can further simplify this and we get this particular form. So now if we just focus on this term, first term, so what is this? This is basically the SNR of the first antenna element, or the SNR of the second antenna element. And then we have 1 plus pi by 4. So you just evaluate this 1 plus pi by 4. This is equal to 1.79 ES by N naught. This is the SNR corresponding to the first antenna element. So from here, what we have observed that in earlier case, when we just directly added the two signals, what we observed that the combined SNR combined was equal to the SNR of the first antenna element and is equal to the SNR of the second antenna element. But here, when we just first estimated the accurate phases and then we added the two signals, what we observed is that the combined SNR is 1.8 times the SNR of the first element. So what it means that the phase rotation has given us a huge improvement of 1.8 times the SNR of first antenna. And if we compare this with the SNR of the selection combining, so in selection combining, what we had is we had gamma. If we have two antenna elements, we have 1 plus 1 by 2, and this is equal to 1.5 times gamma. And if we have, let's say if we have three antenna elements, then we can write 1 plus 1 by 2 plus 1 by 3, and then we have some term here. So we are basically focusing on two antenna elements. So in case of selection combining, we have 1.5 times gamma 1, whereas in cophasing we have 1.8 times gamma 1. So that implies the SNR in case of cophasing is greater than the SNR of selection combining. So that means cophasing is providing us with a higher performance compared to the selection combining, and also the SNR of the single antenna. But what is the price that we are paying in cophasing? In this scheme, the price is that we need to accurately estimate the phases of the channel, that is the rotation that is provided by the channel. And once you have accurately estimated the rotation, then you will get this amount of improvement. But if the estimation is not very good, or if the error is high, then you will not get this improvement in the SNR. So now let us compare this to selection combining and cophasing. So first, the fundamental principle in selection combining is that we select the best signal among the signal receiving at the two antenna elements. So this is very easy to implement. And then the problem is that this is difficult in fast fading, and this is not suitable for continuous time and reception. Why this is so? Because in selection combining, we first have to measure the signal. We require some time to measure the signal. Then we require some time to select the best branch. And then we want to detect the signal X. So we have three stages in selection combining. First, we measure, then we select, and finally we detect the signal. So in case of fast fading, the channel is changing very fast. So it may happen that when in this, let's say here, the channel, you first measure, then you select, but then the channel has changed. So that means you again have to measure, you again have to select, and so you do not have enough time to detect the signal. Or maybe if the channel is changing very fast, then it may happen that what you have selected is not valid for the next time instant. And again, same for continuous time and continuous transmission and reception. So when you have continuous signal, you require some time to measure and select. And if there is continuous signal, when you will measure and select, and then you detect. So this is very difficult in case of fast fading and when you have continuous transmissions. Whereas cophasing, on the other hand, yes, we know that it will require accurate estimates. So we need to have accurate estimates of the rotation provided by the channel. Otherwise, we will not be able to get this kind of improvement from cophasing. But the positive thing is this is effective in all kind of scenarios. So, but what we want to see is what is the best that we can do. This cophasing is definitely providing us with some performance improvement over the selection combining, but our aim is to get the best, the optimal. So that is, we called it as optimal combining, and this we will see in our next video.